And in the case of what we have for proportions, and again, proportion is going to be a statement of equality, okay, between ratios or rational expressions. And for what we have in the case of proportions, okay, so for what we have in the case of proportions, okay, so we have by definition, okay, for proportions, okay, we have that if we have a statement of equality between two ratios, say we have A over B is equal to C over D, and if that statement is true, okay, then you're going to have what will be referred to as proportional cross products, where you have taken the product of alternating numerator and denominators. And so we have A times D is equal to B times C, and this would be with the restrictions, okay, that the denominators be non-zero in value. Okay, so if A over B is equal to C over D, then we have the proportional cross products A times D equal to B times C, with the stipulations that neither B nor D be zero. And now let's say that in the case of what we have as an example of a proportion, and say if we have looking at solving for x, and we have here, let's say we have 2 over x plus 4 is equal to 1 over x minus 3. And for what we have in the case of the restrictions, okay, so we do not want zero-valued denominators. Okay, so x plus 4 cannot be 0. So we have that x cannot be negative 4. And for x minus 3, okay, this cannot be 0 either. So we have that x cannot be equal to 3. So whatever we have for x, we want the solution to be such that we will not end up with negative 4 or 3. And so just looking at taking what we have with the proportional cross products, okay, so if I multiply out, okay, so you have 2 times, okay, the quantity of x minus 3, and we can say is equal to 1 times the quantity of x plus 4. So I'm just mapping together the A and D as well as the B and C items. And we have with distribution, okay, so we have on the left we have 2x minus 6, and to the right again we have equal to x plus 4, and here we have pairs of like terms on opposite sides of the equation. Okay, so let's say if I combine x terms together, so you have 2x and x, and if I proceed by taking out the smaller variable term, which in this case is going to be x, alright, so we're going to have the left hand side will be transformed to x minus 6, and that will be set equal to 4. And if x minus 6 is equal to 4, and I add 6 to both sides, well, we have for the value in x, okay, that is equal to 10. And we have 10 to satisfy both restrictions, okay, not being equal to negative 4 or 3. And for this type of statement, you can sort of go back and check. We have with x at 10, 2 over 10 plus 4 will translate out to 2 over 14. And 2 over 14 is reducible to 1/7. And for what we have to the right, we have 1 over 10 minus 3, and that is also 1/7. So x equals 10 will check out. Now, So I just want to mention this particular part. Now, for what we have in the case of the equations of various types, okay, that involve rational expressions, and working with what we have among the fractions. Once we clear out, okay, we're going to have the development of equations of various degrees, some of which will be linear and some of which will be quadratic equations. And in the case of what we have for number 68, okay, we're starting out with an equation that is expressed in terms of the variable t. And here we have 1/3 minus 4 over 3t is equal to 7 over t. And okay, now for whatever I have for t, I do not want to end up with zero valued denominators. So I don't want 3t to be 0 or t to be 0. And so if there's anything that t cannot be among the apparent solutions, we're going to have 0. So t cannot be equal to 0. And now we have an equation, and I'm going to establish the least common denominator. And the least common denominator will be the smallest term that all of 3t and 3t will go into. So the least common denominator is going to be present already from the second term, which we have at 3t. And I'm going to apply the 3t in the sense not converting all these ratios in terms of the denominator 3t, but where I'm going to use the least common denominator to clear out all these denominators and just put what I have in t in direct terms. So if I carry out the multiplication of the terms by 3t, okay, so you have 3t times 1/3, and we have minus, again we have 3t times 4 over 3t, and we have is equal to 3t times 7 over t. Okay, and you could take at least a couple of different pathways to choose from. Okay, and you have, like, you say we have 3t over 3 will automatically go to t. If you can look at it through the lens of using cross multiplication, then I'll just do the gradual reduction. Okay, so we have 3t times 1 is 3t over 3. We got minus, now 3t times 4 is going to be 12t, and we have over 3t. And we have is equal to, now we have 3t times 7, so this will be 21t, and we have all over t. And again, you can say 3 will go into 3t t times, and we have minus 12t over 3t, so 12t over 3t becomes 4, so we have t minus 4 is equal to, and 21t over t, so this will be 21, and so we have t minus 4 is equal to 21, and there is only one value of t that will satisfy this equation, and that will be 25. Okay, so we have the apparent solution with t is equal to 25, and again the restricted value regarding t is 0, and since 25 does not equal to 0, okay, 25 is our solution. And if our only apparent solution had been 0, which we had violated the restriction that t cannot be 0, then we would have had no solution. But for what we have in t, it does work out. Now, in the case of number 74, okay, so we're going from solving for t to solving for c. And here we have 2 over c plus 3 minus 1 over c minus 3 is equal to 10 over c squared minus 9. And in the last ratio, okay, you can just write the denominator, okay, as what we have resulting from taking the difference of squares and factoring. Okay. So we have 2 over c plus 3 minus 1 over c minus 3. And with c squared minus 9. Again, we have the quantity of c plus 3 times that of c minus 3. And just for what we have in the case of the restrictions. Okay, now again, the denominators cannot be equal to 0. So we have that c plus 3 cannot be 0, which leads to negative 3 being excluded. And as for c minus 3, since that cannot be 0 either, we also have 3 excluded. And for the least common denominator, that's going to be the product of c plus 3 and c minus 3. Okay, and if we multiply the terms out by, okay, the least common denominator, okay, so we have in the setup, if I multiply the first term by the least common denominator, okay, so we can say we have at the start, okay, if you notice, we have least common denominator times the first ratio, so we're going to have c plus 3 to cancel. And if we bring down the subtraction, okay, so I have minus, I have c plus 3 times c minus 3 times 1 over c minus 3. Okay, and if you notice, we have c minus 3, okay, that is going to cancel out. And for what we have in the last ratio, we're going to end up with the complete cancellation of the least common denominator presence. Okay, so we have c plus 3 and c minus 3 to be cleaned out. Okay, so just taking what we have here. Okay, so we have c plus 3 is eliminated. Okay, now we still have 2 times the quantity of c minus 3. And we have next in line, okay, now if you notice, we have c plus 3 was in parentheses, and we're going to have the distribution of subtraction over the quantity of c plus 3. And we have is equal to, and we have 10 left standing. And looking at what we have upon removing the parentheses, so we have for the first distribution, okay, this becomes 2c minus 6, and the next distribution, which would be applying subtraction, or the equivalent of distributing negative 1 over c plus 3, we're going to have minus c minus 3. Okay, we have equal to 10. And so we have 2c minus c becomes c. Negative 6 minus 3 becomes negative 9. And for c minus 9 equal to 10, if I add 9 to both ends, we're going to have that c is equal to 19. Okay, and so we have with this value, okay, we have this amount to comply with both restrictions, that it is not equal to negative or positive 3. All right. Now, okay, so both 68 and 74 lead up to linear equations or first order equations upon clearing out the fractions. And we're going to have a bit of a shift in the gears as we look into number 80. And for what we have in this one, we're once again looking at solving for the variable c. And the first term we have at 4c over c minus 5. We have minus 1 over c plus 1 is equal to 3c squared plus 3 all over the product of c minus 5 and c plus 1. So for what we have here in terms of restrictions, okay, c minus 5 cannot be 0, so we have a restriction that c cannot be equal to 5. And for c plus 1 cannot be 0, so we have the other restricted value at negative 1. And for the least common denominator, okay, we're looking at the quantity of c minus 5 times that of c plus 1. And again, we have an equation, so we're going to clear out all these denominators upon multiplying each of the terms by the least common denominator. So we have, for the first one, that's about, I'll go ahead and just kind of spread this on out. So again, for the next, we have bringing down the subtraction. And we have on the other side, okay, so you're going to have complete cancellation of the least common denominator. Okay, so we have in the lineup, okay, so again we have c minus 5 to cancel, then we have c plus 1 is going to cancel, and for the last you have both c minus 5 and c plus 1 is also, again, going to vanish. So we have in the layout, okay, so you have 4c times the quantity of c plus 1. Okay, then we have for the next, okay, just like what we dealt with c plus 3 earlier. Okay, that was in parentheses, and we had the distribution of subtraction. And so we're going to have likewise, okay, regarding the binomial c minus 5. And we have is equal to, okay, we have 3c squared plus 3. And so looking at what we have after clearing out the denominators, okay, so I have a couple of distributions to perform. So we have with 4c times the quantity c plus 1, so we have 4c squared plus 4c, and for the subtraction distributed over c minus 5, so we have a negative c and a plus 5. We have equal to 3c squared plus 3. Okay, so we have a quadratic equation, and as I look at gathering like terms, we have 4c squared, 4c minus 3c becomes 3c. We have plus 5. Again, we have is equal to 3c squared plus 3. Again, I have a quadratic equation in the variable c, and if I convert what I have here in terms of standard form, okay, so I can combine, okay, the second order terms, and so I have 4c squared and 3c squared, and so I'll just take out the smaller of the variable terms. Okay, so in this case I have 3c squared, and I'm going to take out the constant 3. So we have in standard form. Okay, so we'll end up at c squared plus 3c plus 2 is equal to 0. And looking at what we have upon factoring, okay, so we have with c squared, this will go to c and c. Factors of 2, that will add up to 3. So we have a plus 2 and a plus 1. Now applying what we have with the zero product property. So if I set each of the factors to 0, okay, so for c plus 2 is equal to 0, okay, now we have an apparent solution with negative 2. For c plus 1 equal to 0, okay, I have another apparent solution with c equal to negative 1. Okay. And so just looking at what we have, so for negative 2, this satisfies the restrictions that c cannot be 5 or negative 1. However, for negative 1, okay, now negative 1 does not equal to 5, but we had the violation of the second mentioned restriction. So for what we have as a consequence, instead of having what could have been 2 solutions, we have only 1 instead. Okay, so negative 1 is disqualified. And so for 80, there's only 1 solution for c, and that is going to be negative 2. Okay. Now, for what we have in the case of the next item, and this one is going to be rather tedious, okay, because you're looking at what's going to be the development of irrational roots in the mix once we clear out the fractions. And for what we have in the case of number 81, okay, so we're looking at, okay, start with solving for t, then going to c, and now we're looking at the letter m. And for this equation, okay, so you have m all over 2m plus 1, now followed by the addition of 1 is equal to 2 over m minus 3. Okay, so you have 2 distinct denominators. This time in the variable m, now we're going to have a couple of restrictions. One of which will be that 2m plus 1 cannot be 0, and pinpointing what will be excluded with this restriction. Okay, we're going to have the m cannot be equal to negative 1/2. And with the other restriction, we have the m minus 3 cannot be equal to 0. So we have the m cannot equal positive 3. And we have for the least common denominator. Okay, that's just going to be multiplying 2m plus 1 and m minus 3. And again, this combination is going to be used, okay, to clear out the denominators. Okay, so we have for the first term, okay, so you have again least common denominator. You have times m all over 2m plus 1. Okay, so you're going to have 2m plus 1 terms to cancel. And okay, so you have the next term, that's just 1. You have times 2m plus 1 times m minus 3. So you're going to FOIL out what we have with the least common denominator. And again, distributing the least common denominator once more. So we have with the interaction. Okay, so we have first term, we have 2m plus 1. It's going to go out. And have 2 over m minus 3. So m minus 3 goes out. And for what we have in the setup, okay, so we have m and m minus 3 to multiply. And what I can do for the second set of terms, I can just go ahead and FOIL out the least common denominator. So I have 2m squared and minus 6m we have plus m minus 3. We have equal to 2 over the quantity of 2m plus 1. Alright, so for what we have here, okay, so you still have a distribution to perform. So you have m squared minus 3m, and we have plus 2m squared, and you have negative 6m plus m, so this would be a negative 5m minus 3. And for 2 over the quantity of 2m plus 1, so that is going to be 4m plus 2. And looking at gathering, okay, our like terms together, so you have m squared plus 2m squared. Okay, this become 3m squared, negative 3m, and a negative 5m. So we have a negative 8m. We have minus 3. Is equal to 4m plus 2. So you have a quadratic equation. And if I convert what I have here in terms of standard form, okay, so I'm going to take what I've got. Okay, so we have with 4m plus 2. I'm just going to move those terms over. Okay, so we have 3m squared minus 12m. Okay, we have minus 5 is equal to 0. Okay, now we have with this trinomial, okay, now that one is not factorable. One might be thinking of factoring by grouping. Okay, beginning the process, you'd be looking at multiplying the first and the last coefficients, where we would have 3 times negative 5 would go to negative 15. But again, for factors of negative 15, there are none in the integers that will add up to minus 12. You can have like negative 15 and 1, but the sum would be negative 14 as opposed to negative 12. And the other combination that would result is the negative sum. You would have negative 5 and 3, but that would add up to negative 2 as opposed to negative 12. So we have with this particular quadratic equation, okay, if I apply the quadratic formula, so you have a is equal to 3, b is equal to negative 12, and we have that c is equal to negative 5. And now while I'm solving for m as opposed to x, okay, we're still working with the same premises with the quadratic formula. Okay, so we have a negative b. Okay, so we have the negative of minus 12. We have plus or minus, okay, the square root. Okay, now for b squared, Okay, so you have the square of negative 12. And we have for minus 4ac, so you have minus 4 times 3 times negative 5. You have all over 2a. Okay, so we have it 2 times 3. And for what we have in the layout, okay, say for the numbers inside the radical, now I have negative 12 squared, negative 12 times negative 12, so this would be 144. And then we have negative 4 times 3 times negative 5. For that combination, negative 4 times 3 is negative 12. And then in turn, negative 12 times negative 5 is going to be a positive 60. So the number inside the radical is going to be at 204. And 204 is not a perfect square number, but it is the kind of number where you can reduce its square root in radical terms. So for what we have in the subsequent steps, okay, have the opposite sign of negative 12, so this would be a positive 12. And we have plus or minus, okay, and we have the square root of 204. And we have all over 6. Again, 204, not a perfect square number, but 204 is the kind of number where you can reduce in radical terms its square root. And for 204, okay, a large number, but the largest perfect square that will go to that amount is going to be 4. So in the breakdown, we have the square root of 4. And for 51, okay, there are no perfect square numbers other than one that will go into 51. And so for the reduced radical portion, okay, this will come out to 2 times, okay, the square root of 51. Okay, and now, for what we have in the follow-through, okay, so you have 12 plus or minus 2 times, okay, the square root of 51, all over 6. Now, if you leave the result in sort of a combined form, notice we've got 12, 2 in front of the radical, and 6 on the bottom. So we have even valued leading coefficients. And if I were to factor out 2 from both the numerator and denominator, like 6 goes to 2 times 3. And factoring out 2 from the numerator, 2 will go into 12 6 times. And we have plus or minus. Okay, and 2 will go into 2 times the square root of 51. The square root of 51 times. And so for one version of the results, okay, we have 6 plus or minus the square root of 51 all over 3, and I'll show you a bit of an alternate display. Okay, just starting from here. If I were to go this route, say if I were to separate, so you have like 12 over 6 plus or minus 2 times, okay, the square root of 51 over 6. Okay, what would happen here is that 12 over 6 reduces to 2. And for 2 squared of 51 over 6, okay, 2/6, that part reduces to 1/3. And so with what we have here, if I were to separate the front parts, okay, you have 6/3, which reduce to 2, and you have plus or minus, okay, the square root of 51 over 3. So those would be your possible answers. And let me give you just sort of the notation. If you were to take what we have in Alex, say in reference to 6 plus or minus the square root of 51. If you put it in the combined numerator notation, we have 6 plus the square root of 51 in parentheses over 3. And you have 6 minus the square root of 51 also over 3. If you displayed the division in forward slash notation, okay, and again we have just for the other possibility, and with this notation you would not need parentheses. This would be like 2 plus the square root of 51 over 3. And you have 2 minus the square root of 51 also over 3. So if you intend to leave the 6 and have division by 3, like what's displayed in this compact notation, and Alex, you would have to use parentheses. But if you go with the other notation, okay, you have 2 by itself, and the division by 3 affects only the positive and negative square root of 51. So I just wanted to mention that in terms of the kind of like the syntax that is involved, okay, with the programming concerning Alex. And again, we have irrational roots, and that definitely satisfies the restrictions that m cannot be negative 1/2 and m cannot be equal to 3. And yes, that was a rather tedious problem to work with. And a lot of steps involved, clearing out the fractions, then leading up to a quadratic equation, and then having to use the quadratic formula with radical reductions involved. Okay, a lot of work there. Now for the next item, okay, nowhere as tedious, but just some important reminders. And we have crossing over to solving for the letter Z. And we have for number 82, okay, so for this one, okay, so I have 7 plus 20 over Z is equal to 3 over Z squared. Okay. And whatever we have for Z, we cannot have Z or Z squared to be equal to 0. There's only one restriction, and that is Z cannot be 0. Again, we do not want 0 valued denominators. And for the least common denominator, okay, this would be the smallest term that both Z and Z squared will go into, so that is going to be Z squared. And if I multiply all the terms out by Z squared, and I'll just have the LCD to follow each of the terms originally on display, so I have 7 over Z squared plus 20 over Z times Z squared and you have 3 over Z squared times Z squared. Okay, so just duplicating this, I wanted to mention, okay, so we got first term we have it 7Z squared. Now for 20 over Z multiplied by Z squared, now if you look at it like in terms of cross multiplying, okay, so you have Z will go into Z squared, Z times. For 3 over Z squared, now you're going to have just a complete cancellation of the least common denominator. So we have 7Z squared plus 20Z is equal to 3. Okay, so you have a quadratic equation in the variable z. If I put this in standard form, that is, set the equation to 0. So we have 7z squared plus 20z minus 3 is equal to 0. And I'll just mention, okay, that unlike what we had moments ago in the variable m, we have this particular trinomial is factorable. And I'll just kind of do a quick glance of what we have here. So we have 7z squared plus 20z minus 3. Okay, so if I look at factoring, now remember, you have 7 times negative 3. First last coefficients, you have 7 and negative 3. Multiplying together, 7 times negative 3 is negative 21. And if I'm looking for factors of negative 21, whose sum or difference will be on the plus side at 20, okay, a lot more weights will be given to the positive factor than to the negative. And so in this case, you're going to have the negative factor at minus 1, the positive factor at 21. Again, like negative 1 times 21 is minus 21. Negative 1 plus 21 is going to end up at 20. And it really doesn't matter how you split up the middle term, but I would recommend just having the positive term to come after the negative. Okay, so you have 7z squared. Let's see, we have with the negative 1z at the front, you have minus z. They have plus 21z minus 3. And looking at grouping together. So you have the quantity of 7z squared minus z. And then we have in the middle, okay, we have the operation of addition. And we have the quantity of 21z minus 3. And if we take out the greatest common factor of each pairing, so between 7z squared and z, okay, that's going to leave us with z. And z into 7z squared minus z, this will be 7z minus 1. We have adding, now for the greatest common factor, 21z minus 3. Okay, so that is going to be 3. And the factorization for this second group, okay, we have 3 times the quantity of 7z minus 1. So you have with your factors, you have 7z minus 1, which is shared. And the other factor we have with z plus 3. Okay. All right, so just reverting to what we have with the quadratic equation. Okay, so you have, again, our two factors. So you have 7z minus 1 and z plus 3. And we have in the zero product property establishment, so if I set both 7z minus 1 and z plus 3 equal to 0. Okay, so for 7z minus 1 equal to 0, okay, so I have 7z is equal to 1. So we have one apparent solution with 1/7. And for z plus 3 is equal to 0. Okay, so we have another apparent solution with negative 3. So in looking at what we have in this one, okay, so we have in the overall picture, again, we had the restriction that z cannot be 0, and with both 1/7 and negative 3 as non-zero values, we have in this equation for 7 plus 20z equal to 3 over z squared. That would be true if we have z to be either 1/7 or minus 3. Now, and the crossover. So we've done a lot of factoring and working with fractions, and there'll be a lot of the properties that will be carried over into the next phase. And this will be what we have in the case of radical equations. And for radical equations, there's one key property I do want to mention. That's going to be in reference to even root radicals. And this will be for what we have regarding the principal square root rule. Okay, and for the principal square root rule, okay, this is going to state that the square root and not just the square root, but textbooks commonly refer to just the square root, but it carries out to even roots, period. Okay, so I have square root, fourth root, sixth root, and so on. And again, square roots, it's implicit that what's referred to as the number of the root, that's going to be 2, but 2 is not usually on display. And for the principal square root rule, we have that the square root of an expression cannot reduce to a negative constant. And I'll just mention at the start. Okay, so we have the principal square root rule. Let's call this PSR. It's going to apply to even roots only. Like it would not apply to cubic roots or fifth roots or seventh roots. And let me give you just kind of a backdrop to the principal square root rule. Now, it's kind of a cousin, but it's not the same thing as what we had back when we were looking into the square root property of equality. Now, when you had an equation, let's say like x squared is equal to 36. Again, for that number 2 from x squared, you have possibly 2 solutions. And if we start out with the equation in the form of like x squared is equal to 36, and I applied the square root property of equality, so going from x squared to x, we have plus or minus, okay, the square root of 36. So we had the x equal to plus or minus 6, and so we have for the solutions in x, you would have 6 and negative 6. But now where the principal square root rule would be addressed, let's say just as a cousin to this particular problem where the follow through was with the square root property of equality. If we have, like in the case of solving for x, if we had, let's say, x is equal to the square root of 36. Okay, if you notice, we don't have x to be of second degree from the start. It's just a first order, so likely there's going to be only one solution. And so with x equal to the square root of 36, okay, again, square root of 36, like if you were to enter 36 into your calculator and then take the square root, okay, x would end up going to 6. And if you have something like x is equal to the square root of 100, okay, so in this case, x would be equal to 10 only. And let's say that if I had something like, just in the case of, let's say if we have x in the square root, okay, so you have like the square root of x plus 4 is equal to 7. Okay, so we have the square root of an expression. Okay, like the square root of 36 does not reduce to a negative constant. The square root of 100 does not reduce to a negative constant. So we had respective solutions at 6 and 10. But let's say we have x inside the radical, whereupon we have the square root of x plus 4 is equal to 7. So we have the square root of an expression, and this reduces to 7, and 7 is not negative. So we're going to have at least a solution for x. And so what I can do here is that I can take care of the square root portion if I take both sides and square. So the square root of x plus 4 squared, again the exponent and the radical will take care of each other. To the right I have 7 squared is equal to 49. And if we have the x plus 4 is equal to 49, well, our solution in x, okay, that is going to end up at 45. And say we have just like added cases here. If I have, let's say, we have the square root of 2x plus 5 is equal to negative 3. And guess what? We still have an even root with the square root of 2x plus 5. And guess what? This square root, still an even root of an expression, it cannot reduce to a negative constant. You notice negative 3 is in violation. It's because of the negative sign that we have automatically for x, there will be no solution. And just kind of re-entering, if I have, let's say, the cubic root of 2x plus 5 is equal to negative 3. Again, we have an odd root this time around. And again, the principal square root rule does not apply to odd roots. It applies to even roots only. So in this case, I can free up 2x plus 5. And cubic roots can be undone by taking the radical and cubing out. So I'm going to apply both sides and cube out. So here we're going to have 2x plus 5 is equal to negative 3 cubed. And negative 3 times itself. This will be negative 27. And so for what we're going to have here, taking 5 away from both sides, so we have it 2x is equal to negative 32. And if I divide both sides by 2, it's going to turn out that the value for x is going to be at minus 16. Okay. And tell you what, just for the next few moments, okay, if we look at solving for x, and we'll say that we have here let's say x is equal to the square root of 400. And we'll say we have the square root of 2x minus 4 is equal to 3. And we'll say we have the square root of x plus 2 is equal to negative 10. And we'll say we have the fifth root of 3x plus 7 is equal to 1. Okay, for what we have in the case of trying to solve for x, okay, so we have in the first item we have x by itself in the set equal to the square root of 400. Now 400 is a perfect square value, and again the square root of an expression cannot reduce to a negative constant, and so with the square root of 400, okay, that is going to be 20 only. Now for what we have in the second equation, now we have the square root of 2x minus 4, okay, is equal to 3. Okay, so we had the square root of an expression, in this case the expression 2x minus 4 reduces to positive 3. So there is room to work and find a solution for x. So if we look at squaring both sides, okay, so left hand side becomes 2x minus 4. And we have the 3 squared is equal to 9. Okay, so here we have a two-step linear equation. So if I add 4 to both sides, and I have that 2x is equal to 13. Okay. What do I have for x? Okay, we have a non-integer value. In this case, x be equal to 13 halves if you leave as a fraction, or as a decimal, okay, we have 6.5. Okay. And you can go back and check. So 2 times 6.5 is 13, minus 4 is 9, square root of 9 is equal to 3. Now, for what we have in the third equation, we have an even root radical, but this is said to reduce the expression to negative 10. And since we have a negative value here and we're working with an even root radical, this means we have no solution. Okay, and for what we have in the last of this particular set, we have the fifth root of 3x plus 7 equal to 1. Okay, and if I had like negative 1 to the right, I could still work with this radical since this is an odd root. And now I can take care of the radical, again, taking both sides and raising to the power that matches the index number of the radical. In this case, this will be 5. Okay, so if I take both sides and raise to the 5th power, Okay, so I'm going to have 3x plus 7 is equal to 1 to the 5th, which is still going to be at 1. And we have just following through. If I isolate the x term, upon taking 7 away from both sides, so I'm going to have 3x is equal to negative 6. And we have with division by 3, okay, we come out to x equal to negative 2. All right, now I'll give you a couple more special cases. One of which is going to be where you might have numerical coefficient out in front of the radical. And I'm going to show you just a couple of ways for this one. And let's say that if you have 4 times, okay, the square root of x plus 1 is equal to 7. Okay. What I can do here, I can isolate the radical upon dividing both sides by 4. Okay, so I have the square root of an expression going to positive 7/4. Okay, so we're going to have at least one solution for x. So I can take care of the radical upon squaring out both sides. So the square root of x plus 1 squared, this will become x plus 1. 7/4 squared, 7 squared is 49. 4 squared is 16. And if I get x by itself, so I'm going to take 1 away from both sides. So you have 49/16 minus 1. And if I write this as a difference of fractions, now remember, think of like minus 1 is like minus 1 over 1. Least common denominator would be 16. And so 1 will go into 16 times. So subtracting 1 would be the same as subtracting 16/16. And so for x, I would have 33 over 16. This is one approach. Let me show you the other. Let's say that you don't want to work with fractions from the start. What you can do instead is go ahead and square both sides out. But there's a slight catch to this. Upon squaring both sides, now 4 squared is 16. Square root of x plus 1 squared is going to be x plus 1. Now 7 squared is going to be 49. Okay, now here's the catch. Okay, now if I square what I have here, it's not going to go to the binomial 16x plus 1, because while we have squared the factors, the squaring does not automatically take care of the multiplication that is entailed. So you have not 16x plus 1, but 16 times all of x plus 1. So here, we squared the factors, and then following through completely with distributing 16 all over the quantity of x plus 1. So I'm going to have 16x plus 16 is equal to 49. And guess what? Taking 16 away from 49, so I have 16x is equal to 33. And we have with division by 16, okay, we have, with this approach, we have x to come out to 33 over 16. Okay, so different pathways, but still leading up to the correct solution. And now, if I have, let's say, a couple of expressions in x, and let's say if we have looking at solving for x, and this is going to be a reminder that we have regarding the square root property. of equality. And we'll say we have x is equal to the square root of 4x plus 12. So I have, looking at solving for x, so x is equal to the square root of 4x plus 12. Okay, now if I square both sides, okay, so left side I still have x squared. To the right, we have 4x plus 12. If you notice, we have a quadratic equation that is established. And if I take what I have and write in standard form, so I'm going to join x squared with the first order and constant terms. So we're going to have here, we have x squared minus 4x minus 12 is equal to 0. And looking at factoring, so for x squared, this will go to x and x. Factors of negative 12, whose sum or difference will be minus 4. So we have x plus 2 and x minus 6. And applying the zero product property, one apparent solution for x will come from setting x plus 2 equal to 0, where we have x equal to negative 2. And for x minus 6 equal to 0, then we have the other possible solution for x. We have to be at 6. And now, with even root radical expressions, you don't have to write it out, but if you check your results here, say if I check x equal to negative 2, again, this is our equation. Okay, so you have like x at negative 2, you have equal to the square root of 4 times negative 2 plus 12. 4 times negative 2 is negative 8. And negative 8 plus 12 is going to be 4. And guess what? Square root of 4 is going to be at 2. And we're trying to say that negative 2 is equal to 2, so that is going to be false. And you already have with negative 2, you already have the violation of the principal square root rule. So negative 2, that's going to strike out. Now, as for what we have in the case of x is equal to 6. Okay, so we got the same equation, different value of x to plug in. Okay, so you got x at 6. Then we have the square root, and we have 4 times 6 plus 12. Four times 6 is 24, plus 12 is 36. And it's kind of showing you incrementally, step by step. Now the square root of 36 goes to 6. And we have that 6 is equal to 6. So x equals 6. Okay, that is going to check out. So for this particular type of equation, okay, we have only one solution, and that is going to be with the number 6.